Okay, for our first screencast assignment, a couple things to keep in mind. First of all, you're going to be taking notes for this. In order to get credit for it, you're going to be taking notes for it in one of your composition books. If you have one that's got graph paper in it and one that doesn't, I prefer you to use the one that doesn't have graph paper in it for this. But either way, you want to make sure that this is in a composition book and has your name on it. It's prepared to be turned in or checked at any time. Bring it with you to class every day. So that composition book should be with you every day, because if we take notes in class, I'm going to have you put it there as well. Okay, so what we're going to do is we're going to start off with just a quick review, hopefully. Well, it may not be a review. If you've had possibly some trigonometry, if you did the summer assignment and were exposed to it, you've seen this a little bit, I recommend that you watch it again, because you can never go over this enough, too many times. So, what we're talking about here is right triangles. So first and foremost, right triangles. Like so. Right triangle, of course, is a triangle in which one of the angles is a 90-degree angle, indicated by a little box. We will generally, if there's no other classification of the sides will be classified as the longest side is the hypotenuse and is called lowercase c, and the other two sides are a and b. It really doesn't matter which ones are which. I'll call lowercase a, lowercase b. And if there are no other ways of describing it, the angles have the same letters but uppercase, and there's an arrangement here. So you see side C right here. It is opposite, in a triangle, it is opposite angle C, which is always the 90-degree angle. If you think about it, the biggest angle in a right triangle is always going to be the 90-degree angle. These other two angles, we'll call them, let's see, this one should be angle B because it is opposite side B. And this would be angle A because it is opposite side A. The other two angles will always add up to 90 degrees, of course. They will be what we call in math speak complementary. Or if I say the complement of. So for example, in a right triangle, B and A, the angle B and angle A, are always complements of each other. If one of them is 30 degrees, the other will be 60, and so forth and so on. And for the record, as we go through this demonstration, I have one triangle here. I may at times use all kinds of interesting numbers, like 10 degrees in one of them, and 80 in the other. Even if they don't, this angle is certainly not just 10 degrees, and this one's certainly not 80, but for reference purposes, we'll just run with it, just buy it. So the drawings will not always be to scale, we would say, but I'll try to keep it somewhat reasonable. So that's a math way of looking at it. What's interesting about this situation is this, is that even if we took, let's say, angle A here. So if we stood here at angle A and somebody asked you, hey, from where you are in this corner of the triangle-shaped room, right? Triangle-shaped room here. If somebody asked, you're standing in that corner of the room, what side is opposite you? And we already mentioned that would be this guy. So for angle A, important to note, this is the opposite side. For angle A, this would be the adjacent side. Well, what's this? Well, that's the hypotenuse. And that is the same for no matter where you are, whether you're standing at A or whether you're up here at B. The hypotenuse is the hypotenuse. It's the longest side. But think about there for a second. If you're at B, that means that your opposite, if you're standing in that corner of the room, this is the opposite side for that angle. So it depends on which of the two angles, A and B, you're standing at. And if you're wondering, well, what about C? Don't do it. C, it's right out. It's a 90-degree angle. It's opposite the hypotenuse. Leave it alone. These trig functions are going to work for the other two angles, A or B. And for B, this would be the adjacent side, because this is the hypotenuse for both. So we have these descriptions of the sides. Okay? So, what I want you to consider, I'll fix that, is this. You got, this is B, we don't forget that. Now, if you are considering this angle, let's say you draw in here another right triangle. You drop a line here, you have another right triangle, or you can do another one here. Those triangles in geometry would be similar. In other words, the black triangle would be similar to the blue, and which would be similar to the red. In other words, they all have the same shape, we'd say, but it's just a matter of scale. One has been increased by a factor of multiplying by 2 or 3 or whatever. It's just a number has been multiplied or divided into all the dimensions, and it's been shrunk or enlarged. That means that while the red side will say here, while this opposite side is definitely shorter than, let me get a pointer here, so while this red side here is certainly shorter than this right here, and of course longer than B, so they have different, these side A's would have different sizes. If we compare them, so you take this red and you compare side here, side A in the red, and you were to say compare it to the, let's say the hypotenuse of red, this length here, you would actually get the same comparison or the same ratio that you would if you took this side, the black side here, and compared it to its hypotenuse. That those ratios would always be the same. So those ratios always being the same for a particular angle, notice we didn't change this angle. That's a significant, useful fact. So we give it a name. That ratio that we just talked about, where we talk about the opposite, see we're talking about the red angle, so that would be the opposite and the hypotenuse. When we compare those two, let's put the opposite on top. So if I can take the opposite and I divide it by the hypotenuse, I'll get a number. If I do the same thing for angle A, but for the black triangle, if I take its opposite and its hypotenuse, which would be from here all the way to here, if I do its opposite in hypotenuse, I'll get the same number when I'm done dividing. In the same way, if you keep in mind that if you take 1 divided by 2, you'll get 0.5. But if you do 4 divided by 8, you'll get, well, 0.5, right? It's just a matter of increasing both of them by the same factor. You would still divide and get the same thing. So if we look at an angle in a right triangle, and we consider the side opposite that angle, and the hypotenuse, that ratio for that particular angle, maybe it's a 60-degree angle, maybe it's a 58, whatever angle that is, that ratio will always be the same. So we would say that the sine of angle A is equal to the, or any angle, is equal to the opposite over the hypotenuse. Oftentimes, instead of A's, B's, and C's, you'll run across the Greek letter theta for angles. That's a common occurrence. It doesn't really matter what the name of the angle is. The sine is always opposite over hypotenuse. Okay, moving on. Then if we, how do we define the cosine? Well, once again, we got angle A, angle B, angle C. For still working on angle A, just pick an angle and stay with it. For angle A, what would the cosine be? Well, it would be the ratio, so the cosine of angle A would be the ratio of the adjacent side to the hypotenuse. What about the tangent? Well, think of the one combination we haven't gotten yet. We've done opposite in hypotenuse and adjacent in hypotenuse. There's one left, the one that doesn't use the hypotenuse. Tangent of A would be its opposite over its hypotenuse, not hypotenuse. See, I got myself all excited there and made a mistake. Opposite over adjacent. So then you might be asking yourself, well, great, but how am I going to remember all that? People over the years have come up with a way to remember it. Actually, this was not around when I was in high school. That's how old I am. If you want to remember how to define the sine, cosine, and tangent, let's see. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. SOHCAHTOA. Okay, it works for people. I'm not saying, whatever, but if that helps you remember it, SOHCAHTOA, then you're trying to figure out which ones to use when. This is your thing you want to go to. So, moving on. Let's see how we would use this little fact. So, by the way, your calculator can tell you the sine of, let's pick a random number, of a 17.3 degree angle. That is a specific ratio, unique to a triangle where this angle, for example, would be 17.3 degrees. That is a value that you can find in a calculator. When I was in school, we had to look it up in tables in the back of a book, but that's beside the point. I'm not kidding, we did. So, if you know the angle, then you already know that ratio, and we can use this. So here's how we would use it. Let's pick some pieces of this triangle to know. So let's say we know this is I'll try to keep it realistic, a 53 degree angle. And let's say that we know the hypotenuse is, I don't know, 1.8 meters long. I'm a physics person, I'm going to put units in. From just that information, and we'll label our angles as, angle C, angle B, angle A. From just that information, we have enough now to find the length of that side, the size of that angle, and the length of that side. We can find those three pieces from just the information given using these ratios that we've talked about. So, let's go through and see how to do that. You may have ideas of where you want to start. Probably the easiest thing to find would be the other angle, because we know that this angle, angle B, and angle A have to add up to 90 degrees. So if I take 53 from 90, I'll get, let's see, 37. And here's my suggestion. Even though I found it first, it's kind of a danger, because you want to stick to one angle. You don't want to mix angles halfway through, you'll confuse yourself. So for this rest of this problem, we're just going to use angle A and 53 degrees. I'm going to refrain from using this angle, because what if I made a mistake and wrote 27 or 47? What if I confused myself and didn't quite do the arithmetic right? And then I use a wrong number. So in general, when you're solving the pieces of a right triangle, try to always use the original given information. You're less likely to compound an error. If you make a mistake and then you use a number to calculate something else, and you're going to get another mistake. So, word of advice. So let's figure out what this is. So I want to go after that green one. So the first thing I got to figure out is, well, what information am I given and what am I looking for? So for example, for the 53 degree angle here, we already know this is the hypotenuse no matter what. For the 53 degree angle, this is the opposite side. And down here would be the adjacent side for that angle. But I don't care about adjacent right now. That's not what I'm looking for. I have hypotenuse, and I'm looking for opposite. And I got to think, what trig function relates those two? I go back to SOHCAHTOA, and I think sine is opposite and hypotenuse. Bingo. So I'm going to use the sine of angle A to figure this out. Now, what is the sine of angle A equal to? It's equal to the opposite. Okay, I don't know that, so I'll just write down, for temporarily speaking, let's call, I know what I want to call that. That is little side A, right? That's the letter I should use. So that is the side of the opposite, sine of A is equal to the opposite side, little a, over the hypotenuse, which is 1 point, well, we'll just write down hypotenuse, which is, yeah, you know, let's do that. Let's write opposite for a second, just so it's all clear. Now, that means, remembering that this is what the sine is about, that the sine of a 53-degree angle, of our 53-degree angle, is equal to little a, the variable for that side, because I don't know it, over the hypotenuse, which is 1.8 meters. So now I have to solve for a. Not a big deal. I'm just going to multiply both sides by 1.8. So a is going to be 1.8 times whatever the sine of 53 is. So I go to my calculator. I don't want this, so I'm trying to get rid of it. Well, whatever. Just go away. There we go. We'll just do it this way. So I'm going to take 1.8. Fighting with the computer. Hold on. 1. There it is. 0.8 times. In this calculator, I'm going to have to type 53, then hit the sign, and then hit equals. So I get a value for A that is 1.438. Probably too many decimal places, but we'll go with it. So A is 1.438. Is that what I said? Yeah, 1.438. Okay, meters. Now, I got that one, check. I could, if I wanted, use the Pythagorean Theorem with 1.8 and my new value, but remember what I said, I trust it pretty well, but I'm not going to use that. I'm going to try to figure this out using the original information, using the 53-degree angle and the 1.8. So I have now got to figure out, I got adjacent and hypotenuse. So which trig function is that? Give you a second. Adjacent and hypotenuse. Correct. That would be the cosine. So the cosine of angle A is going to be equal to the adjacent over the hypotenuse. And in this case, that means the cosine of a 53-degree angle is equal to the adjacent, which I don't know, that would be technically called lowercase b, over 1.8. And so, in a similar fashion, I find out what b is. I multiply both sides by 1.8. So 1.8 times cosine of 53 and I get 1.083. And I now know all the pieces of this right triangle. I know the length of this side, I know the length of this side, and I know the hypotenuse, of course. And I know all three angles, 90, 53, and 37. If you really wanted to check, you could see if everything matches fairly well to Pythagorean Theorem, which is the hypotenuse squared equals the sum of the squares of the two legs. So you could do that squared plus this squared, and see if it equals 1.8 squared. All right, moving on. Let's see if we can use the trig functions to solve this scenario. So we have some building over here whose height we want to determine. We'll call that height, I guess I'll call it just y. That works. All right, so I don't know the height of this building, and I want to try to figure it out. So I can't climb the walls, but I can walk this distance. So I can go from here to here, and with a tape measure, and measure that. So let's say I measure that to be 21 meters. Is there a right triangle in here? Well, if we assume that our building is vertical, we have a right triangle. The thing is, we're gonna measure from here. So my right triangle, I'm going to say, this is some sort of a tabletop or something where I'm going to put a device, and I'm going to look at the edge of the roof there. Look at that. And then what I'm going to do is that device is going to measure the angle for me. It's going to tell me this angle, what they call the angle of elevation. So actually my right triangle for this problem is going to be this one. I'll put it in a different color. It's going to be right here. So as an aside, I'm going to point out right now that you would want to know this because you're going to have to add it on later. So let's say this is 1.2 meters. We'll come back to that. But for now, I need to find this side of that right triangle. Well, what do I know? I know this side. I know that's 21 meters. I know this angle. I have a device to let me measure that angle. I'm going to say it is 28 degrees, we'll say. So I measure about 28 degrees. And I'm after this. Because if I find that, all I got to do is add on this little 1.2 meters at the end, and I'll know the height of the building. So let's see what we got. So what side is this thing over here? For angle 28, for the 28 degree angle, what would we call this side? It would be the opposite. Alright, where's the hypotenuse? Well, that's going to be the longest side. It's going to be this one right here. And what about the adjacent then? I always do them in that order, by the way. I do the opposite. It's easiest to find. Hypotenuse is the next easiest because it's opposite the right angle, and the other one's the adjacent. So I have the adjacent, and I'm looking for the opposite, and I could care less about the hypotenuse. So I need the trig function that's going to help, that's going to give me or relate opposite and adjacent. So you go to your SOHCAHTOA and see if you can pick out which one it is. Well done. It's TOA, right? The tangent of our 28 degrees is going to equal the opposite, which I don't know, we'll call that y, over the adjacent, which is 21. And so I'll do 21, so y is going to be 21 times the tangent of 28 degrees. So I'm going to do 21 times tangent of 28, so it's 11.17 meters. So 11.17, that would be the distance from here to here. So the opposite side is 11 point, I forgot what it was, 17. Now in this case, if I want the true height of the building, so I guess I really shouldn't use y, right? Because technically I wasn't really fine using y. That's this side. The y is all the way down. So I'll call it, oh, what the heck, I'll just call it opposite. There we go. Now to get y is going to be that opposite side that I just found plus the 1.2 that I started from. And so it's going to be, the total height of the building is going to be 11.17 meters plus 1.2 meters. And that's going to be 12.37 meters. Okay. Another application, real quick. Let's say you want to know how wide this river is, or you want to approximate how wide this river is. So you see a tree. This represents a tree, by the way. It's my attempt. On the other side from where you are, You really want to know this distance, how wide the river is, but nobody wants to, jump in and swim it with a tape measure. But if you position yourself here, put a stake or something, or mark that spot right across the river from the tree, and then you walk down a known distance. You get your tape measure out, you walk this way, on nice dry land, till you get to like here, somewhere else. And then, if you can line up your measuring device and measure this angle, there's surveyors use instruments like that all the time, called a transit, to measure that angle, so you can find this distance. So notice it's actually setting up just like the other problem, where this would be the hypotenuse. If we're talking about this angle, which I'll call 43 degrees, and I walked this distance with a tape measure, so I'm going to call it 7.6 meters, then I can find this, which is the opposite side. Right. And in this case, I'll just call it W for the width of the river. And so it's just like the previous problem. In fact, I encourage you to see if you can finish this problem, because it's done just like the previous one. You don't even have to worry about this little thing that you got to add on at the end for that one. Here, once you get your answer from the trig function, solve that, you're good, you're done. Here's where we would use something like this when it comes to vectors. So we're going to have a vector here. Hold on a second. So we're going to have a vector. This black line right here is a vector called V. And this orange line represents its x component. And this purple line represents its y component. Do you see a right triangle in here anywhere? Well, you do. You might not realize you see it, but it's there. If I took this, made a copy of it, and I slid it over to there, see the right triangle now? We can create right triangle if we just slide the y component over, so we can kind of get a feel for what right triangle we're talking about. So I have a right triangle where the hypotenuse is the magnitude of that vector. This would be the x component. I'll call it v sub x for the vector, and the purple here is the y component. Okay, so let's say I know the x and y component. Let's say I know that the x component is 0.8. Doesn't matter what the units are right now. Let's say the y component, let's see, is going to be 0.35. 0.35. What's the magnitude of this vector? In other words, what is the length of that? Well, it's just the hypotenuse. In this case, we don't need a trig function, because, not for the hypotenuse at least, because we can use Pythagorean Theorem, which says that, remember, a squared, technically this is like a right here, a squared plus b squared equals c squared. Right? The two legs squared, so I can write that the x component squared plus the y component squared has to equal the magnitude of the vector, the overall length of this arrow, right here, the magnitude of that vector, the length of that arrow, squared. It's just Pythagorean theorem. If I take the square root of both sides, then I have the, quote, formula for finding the magnitude of a vector. It is simply going to be the square root of the x component squared plus the y component squared. So in this case, the length of that arrow is going to be the square root of 0.8 squared. Technically speaking, y component should be negative, right? Look where it is, it's down. I've got to be careful, that's down. So that's going to be negative. It won't make a difference here because we're going to square it, so be careful on your calculator, because sometimes if you don't enter it right, it'll give you a negative answer. But so I'm just going to say plus 0.35 squared for now. the negative's not going to be important. It'll be important when we get to the angle at the end here. So I'm going to take 0.8 squared plus 0.35 squared, get an answer, and then take the square root. 0.873. Makes sense. So that's part of the deal. Now what about this angle? I want that angle right there. I want the reference angle, the angle between the vector and the x-axis. I don't want this angle. No, I don't want that angle. I want this angle, the one between the vector and the x-axis. So for that angle, even though I know the hypotenuse, I don't want to touch it, because what if I made a mistake? I'm going to use the y component, which is the opposite, correct? And the x component, which is the adjacent. So opposite and adjacent. Which trig function are we talking about? Bingo, it's tangent. So the tangent of our angle, I'm going to call this angle theta with a little r for reference angle. So the tangent of our reference angle, which I don't know, is equal to the opposite, which is going to be the y component, over the adjacent, which is the x component. Once again, I'm going to ignore the negatives. Just use the positive values. We'll let the picture tell us what to do in a moment. So I'm going to solve this for theta. But how the heck do you do that? Well, here's what you do. You notice on your calculator, if I hit, see where tangent is there, right? I can't really point at it too well, but you look on the calculator, you'll see where tangent is. Now you're watching tangent, and I'm going to go over and push the button up there that says INV, inverse. So I'm going to go over and push the inverse button and watch what happens to tangent. Okay, wait, didn't do anything because I have the thing here. Hold on. Now I'm going to do it. Boom. There it is. And all of a sudden, you have something that looks like this. Tangent with a little -1 there. That is the inverse tangent. You can use that if you know the value of the tangent, or you really could use it for any trig function, but then you can use it to finally go back and figure out the angle. So for example, the inverse tangent of the y component over the x component will give me the angle. So that would be the reference angle is going to be the inverse tangent of the y component, which is, remember, I'm not worried about, right? I'm just using positive values here. So y component is 0.35, there we go, divided by 0.8. Take the, did I do that right? Yes. And then take the inverse tangent. So I'm going to go to the calculator. I'm going to go 0.35 divided by 0.8, get an answer, then hit inverse, which is already selected, tangent. It'll be 23.6 degree angle. So the reference angle is a 23.6 degree angle. This angle right here is 23.6. Now, another way to describe that angle might be to start from here and go all the way around to there. Don't panic, it's not a big deal. If I went all the way around to here, I'd go 360, right? All the way around. So take 360 minus 23.6, and I'll know the green angle here, this long way around here. Right, so that green angle is going to be 360 minus the 23.6 degrees. Or you could say, now here's the way you would describe it. For that vector, the final answer would look something like this. So that vector would be, V is equal to 0.873, that's its magnitude, at an angle of, now you got some choices, you could say, really three choices I can think of. You could say 23.6 degrees, fourth quadrant, quadrant 1, quadrant 2, quadrant 3, quadrant 4. Or you could say, let's see, 360, that's going to be 336.4, I believe. If if I subtract it from 360. That would work. Or you could even say negative 23.6, and most people would know what you meant. You start here and you went the other way. But that would be your vector in magnitude angle form using trigonometry. All right, I'm going to hold it there. Here's what I want you to do. I'm going to give you this as negative 8. I'm going to give you this one as 19, negative 19. And I want you to find, I'll call this vector v. I want you to find me vector v's magnitude, and I want you to find the reference angle, this angle here. Okay. I'll be looking for that when I see your notebook. All right. This is it, and thank you very much. Thank you very much for paying attention.